Hi, welcome to today's video about the Muon g-2 anomaly and a potential hint for a fifth force in physics. This is a nice picture. It shows you the formation of the muons. A proton from the cosmic background radiation hits a molecule of the atmosphere. Then you get an anti-pion, I-. It decays then to a muon. The muon has a negative charge. Antiparticle is a pion with a positive charge, and the muon has also an antiparticle. That's the anti-muon with a positive charge. And muons and anti-muons are unstable subatomic particles. The muon has a negative charge and has a mass of 207 electron masses. This is a picture of Sudan 2. This is located in the Sudan mine in northern Minnesota in America. The muon detector is on the right in this picture. This is how the muon decays. It has a lifetime of just 2 microseconds. It decays into an electron, an anti-neutrino, and a muon neutrino. The muon experiences time dilation. This is an effect of special relativity. That's the reason why, despite having such a short lifetime, secondary muons with their speed near the speed of light can reach the Earth's surface, because time goes slower for a muon. This is the standard model of physics. It contains subatomic particles. There are 2 big groups, fermions and the bosons. Fermions have a half-odd integer spin, for example 1/2, 3/2. Bosons have an integer value spin, 0, 1, 2, for example the Higgs-Boson. And there are baryons. These are composite particles, for example the proton is a composite particle of 2 up quarks with 2/3 positive charge each, and 1 down quark with -1/3 negative charge. And the neutron is a composite particle of 1 up quark and 2 down quarks. Then you got here leptons, for example the electron neutrino, and here is the muon. This is the strongest force in physics, strongest of the 4 fundamental forces. That's the strong force. In this picture, this example of the neutron. It is made of 1 up quark and 2 down quarks. The particle between the quarks is the gluon. This is the exchange particle. The gluon holds the protons, the neutrons, and the atomic nucleus together. The strong force is the strongest of the 4 forces. It has a very short range of 10 to the -15 meters, 1 femtometer. And in this picture you can see the color change. That's the color charge change. And the theory that describes this charge change is quantum chromodynamics. It's a very beautiful picture. It's an example of electromagnetism, which is the second strongest force, fundamental force. This is a picture of ferrofluid under oil in a magnetic field. This is the weak force. This is the 3rd strongest force in physics. This is relevant for nuclear fusion and fission. One example is the beta- decay of tritium. The weak force has a very short range of 10 to the -18 meters. That's less than the size of a proton. This is a very beautiful picture of the Andromeda galaxy. You can see 2 of its satellite galaxies. At the top, that's M32. And at the bottom, that's M110. This is one example of the weakest of the 4 fundamental forces. That's gravity. It is dominant in big scales, cosmic scales. Gravity has unlimited range. The Andromeda galaxy contains 1 trillion stars. But the combined mass of the stars and the planets and moons, the bright matter is not enough to hold the structure of the Andromeda galaxy. That's why, according to the current theory, there is also dark matter that's relevant for the structure of this galaxy. This is a picture of the Fermilab Muon g-2 experiment. G is the magnetic dipole anomaly. This experiment, this machine contains kicker magnets that can direct muons with their negative charge. This is the CMS, the compact muon solenoid at the Large Hadron Collider. The magnetic dipole anomaly has a value of 2. This is a picture of the detector. These are at the bottom lead fluoride crystals, and at the top that's silicon photo-multipliers. G-2 is a precision, gives you a precision of the value G. There's a new measurement that shows G-2 at 0.20 parts per million. That's a double improvement in precision. There's a minimal discrepancy between the measurements and the standard theory. And in future measurements show that there is a discrepancy. Then this is a hint for a fifth force in physics. This is confirmed. This is a picture of the straw detector. These are straw ionization chambers filled with argon and ethane, and they have a cathode wire in them. This is one example for muons in atoms, this muonic helium. You can see here the core of the helium, 2 protons, 2 neutrons. However, 1 electron is replaced by a heavier muon. And because since the muon is heavier, it is much closer to the nucleus than to the other electron. So it is more part of the nucleus than the shell. That's why this muonic helium reacts like hydrogen and not like helium. But again, you have this short half-life of 1.52 microseconds of the muon. Then there's also muonic hydrogen. That's a combination of a proton with a muon. And there's also a known muonium. That's an anti-muon in the center that is orbited by an electron. All these species are known. And one other thing about the muon, since it is so close to the nucleus, that makes the nuclear fusion much more probable. That's why muons are catalysts for the nuclear fusion. However, there are practical problems for an application. One problem is the short half-life of the muon. And second is you have to generate these muons. And that's, but in general, it works. This is a nice picture of radioactivity and radiation on Earth. You can again see the cosmic protons hitting the molecules of the atmosphere. Then you get the antipions, muons, and the pions. And at the bottom you can see examples of the radioactive isotopes of uranium, thorium, potassium-40. Potassium-40, one famous example is the banana. Contains a higher concentration of potassium. And another isotope is radon. And the natural radioactivity with its low dose is an important driving force for mutations. And mutations are important because they allow evolution. Evolution is if life adapts to new environmental conditions. There are 3 types of radiation. That's alpha radiation, that's helium-2 plus helium core. Beta radiation, these are fast electrons. Gamma radiations are fast photons. This is a nice animation of the dark matter distribution around the Milky Way galaxy. There's an estimation that the universe contains 68% dark energy, 27% dark matter, and only 5% bright matter. And the dark energy and the dark matter must exist for explaining the universe as it is. Dark energy drives the expansion of the universe. Dark matter holds the galaxies together and gives the universe its filament structure of the galaxies. but it is not known yet what dark matter and dark energy is. This is still open question. This was today's video about the Muon G-2 anomaly. Thank you for watching. Have a nice day. Bye bye.